Hello, my name is Martin Neukom. I'm one of the developers of the Paios measurement system, and I would like to give you an introduction to the Paios measurement platform. Before we start, I would like to share with you some basic considerations about research. In our view, research always works in cycles. So we produce a certain device and then we measure it. Now we need to learn how this device works, why it works especially good, why it doesn't work good at all. And once we have understood the device, we can improve the device and find a new structure that is better and restart the research cycle. And in this way of understanding how the device works, we usually need additional experiments. So we do, in this case here, experiment 1 to measure the mobilities, and then we do experiment 2 if we still don't understand, and we move on to experiment 3. And the basic problem now is when we're working with organic semiconductors or with Perovskite, for example, all these kind of materials and these devices are not very stable. So when we did experiment 3, 2 weeks later, when we did experiment 1, the device may have degraded in the meantime. Another disadvantage here, of course, is that you need a lot of different measurement systems and a lot of people and a lot of time. That's why we came to the idea to make a platform that includes everything in one and measures everything at once. This is what we call the Paios research cycle. So you connect your device once, Paios measures all the characterizations that are available within a few minutes, and then you go to the part of understanding and just browse through your data, analyze it, understand, and then you can go on to produce your new device once you have understood how it works. Paios comes in 2 different versions, one for solar cells and one for OLED. In the case of a solar cell, you have a light source that illuminates the solar cell bottom up. In the case of the OLED, it's the other way around, and the OLED produces the light, and we use a photodetector to detect the light. Here you see the Paios measurement system. It has dimensions of 40 times 30 times 20 centimeter. And here you see the Paios connections. So here the LED is connected, the photodiode, and here the device. There is an option for multiplexing, and in the case of multiplexing you can connect 4 devices in parallel. Here you see the measurement table of Paios with the LED that is here below. And we now connect a test solar cell to make some test measurements. This solar cell is a microcrystalline silicon solar cell, and you see the surface is quite small, it's 9 square millimeter. We developed this magnetic contacting probes to have a flexible contact and to have a contact that is well suited for transient measurements. A good contact is the key for a good transient measurement. When Paios is started, you first see this welcome screen. Here you see that the system has been initialized and you see which of the numerous modules are available. You can choose from different templates or select your most recent. I now just start with an empty file for solar cells by clicking here. So this is the main Paios GUI. Here in the tab Measurement Procedure, we can define an experimental list of experiments that we want to measure quickly after each other later on. I now just add an IV curve, so I go current voltage characteristic and select ramped current voltage characteristics. Here I can define the light intensities that is used, so now 3 times an IV curve is measured with 0 to 100% light intensity. Here I can define the voltage range, and let's just perform a test measurement. Now you see the solar cell is measured, and that's already it. You see, this was in real time. These IV curves are measured quite quickly. Once you're here, you can now look at your data and browse through it. So you see the 3 light intensities. You can plot them in log if you want. And there is different quantities here that you can look at. For example, here you can also look at the cell power. Let's now move on and add another experiment type. I would like to measure an IV curve, but here advanced. So what is done here, an IV curve is measured with 20 different light intensities, so the light intensities varied from 0.5% to 100% in 20 steps logarithmically. When I start measurement, here again we see the preview window. We now can look at the cell and we see how the cell is illuminated bottom up by the LED. And with each time the LED gets brighter, because we now measure different IV curves at different light intensity. So the measurement has now finished. We can now again browse through the light intensity, here browse through the data. And I did this measurement because I would like to show this plot here, VOC versus light intensity. When we plot it in linear light intensity, linear scale, then we see this logarithmic dependence. And when we plot it here in log, we see that it's really perfectly linear. This is like the theory predicts for microcrystalline silicon solar cell. Of course, there's also plenty of other views that you can choose here from. Let's now continue with transient measurements. Here we added a JV curve before. Now I would like to add a transient photocurrent. Here the cell is flashed with a light pulse. On this graph here you see a preview, so you see the light pulse, and what I do now is I vary the light intensity, but I want to make a light pulse quite short, so I make it 10 microseconds and 5 microseconds waiting time before and afterwards. Let's now start to see how it works. Perfect. When we now look at the current, you see the current for these different light intensities. You see how the current goes up and how the current goes down. Okay, so let's now add 2 more experiment types before we move on. I now would like to measure one C-leaf curve. There's different kinds of C-leaf here. I now choose C-leaf with light intensity variation. Here I can choose the end voltage. I choose it to 2 volt, and what is varied here is the light intensity before the light pulse. So you see here the light intensity and here then the voltage ramp. Paios now adapts the open circuit voltage at the beginning here such that no current is flowing. So when I now press start measurement, you see the voltage is automatically adapt such that here the current at the beginning is 0, and you see now all the curves being measured for the 8 different light intensities. And this is now the result. We can again browse through the data. So you see with a high light intensity we see this nice overshoot, what is typical for C-leaf, and by going to lower light intensities this overshoot gets smaller and smaller. C-leaf measurements are frequently used to measure the charge carrier mobility, and Paios also does some automatic mobility calculations. This is based on this position here of this current peak, and we now here can plot the mobility versus the light intensity. So you see here the mobility is constant to a certain part, and then with increasing light intensity the mobility is decreasing, or seems to be decreasing. This is the case because here the peak moves a bit to the right when the light intensity increases, and this is just due to the fact because more charge is extracted and that takes a bit more time. So in this case here this mobility in this range here would be the good one. Let's now add to the end one impedance spectroscopy measurement. Here I choose to go from 10 MHz to 1000 Hz in 30 steps. And let's now start. So the system starts at 10 MHz, and in principle it's capable to measure down to 1 Hz. Okay, the system has now completed. Now you can choose here between different ways of plotting impedance spectroscopy data. Very common is this cold-cold plot, or what is often used is to plot the capacitance versus the frequency. So here we see the frequency and here the capacitance, where this here is probably the geometrical capacitance that is here decreasing due to the series resistance, and here to lower frequencies increasing probably due to traps. Now we have made ourselves here a measurement routine with 5 different experiments, and we could now go on to acquire and manage data to add here a device and measure all of these techniques at once quickly after each other. To do so, I start with adding a new sample. I name it test sample, and now I add a device to this sample, and I call this device test device. And now I can press start. Now all the measurement experiment types that we defined before are now measured automatically after each other. We will now speed up the video a bit so we don't need to wait for the measurement to be finished. Okay, there we are. The measurements have now been completed, and we can now go here to test device and have a look at the measurement data that has just been measured, and here we can now browse through all the measurement data. Now I have connected an organic solar cell, and I would like to measure this to compare it afterwards with our microcrystalline silicon solar cell that we measured here with test device. So I just add a new device to our sample. Name it OPV1, and the surface here is a bit larger. It's 0.3 centimeters square, and here we go. Again, we speed up the measurement so we don't need to wait the full time. The measurement is now completed, and here is OPV1. We can have a look at the IV curves here as an example, or we can have a look at these IV curves or at the transient photocurrent. Now we have stored our measurements in a database, and we are able to compare these two data sets directly here in the software just by selecting several, and here we can now play with these IV curves and tuning the light intensity and see how these IV curves here of the two cells behave differently. And we can do this for all the experiments that we have performed now. And since we have performed it with the same settings, these experiment and measurement types are also directly compatible. For example, we can look at VOC versus the light intensity, and we see that the microcrystalline silicon solar cell here has a very straight linear behavior with the light intensity in log, and the organic solar cell here has a different behavior at low light intensities. We can also look at the transient photocurrent here and see that the organic solar cell, the rise time here is much slower than in the case for the microcrystalline silicon. Also in PhotoCLIF we see distinct differences. Now I would like to add a third cell, so again click here, add new device. I now connected a cadmium telluride solar cell, and again I will press start and everything is measured after each other, and again we will speed up the video so that we don't need to wait. The measurement has finished, so let's now have a look at the results. So here's the cadmium telluride cell, and when I go to transient photocurrent, here you see that the current rise looks completely different compared to the two other devices. So I can now select all devices together, and we see that this rise here in current when we flash a cell with light is completely different, what means that the charge carrier dynamics here are really different. And these charge carrier dynamics we only see in transient measurements when we compare the IV curve like here, we cannot distinguish here the charge carrier dynamics. We see that the IV curves are different, but to learn more about charge carrier dynamics, like mobilities, charge trapping, and so on, we need to go in the transient domain. Once we have found some results that are interesting for us, we can add them to so-called key results. So let's, for example, add this here, or I could add this VOC versus light intensity here. Or I could also add just like one single cell. Add this here. When I go to Key Results tab here on the right, I will see a summary of all the key results I have exported. And here I can now export my study as a PNG or as text file or as a vector file, and include it then later in a report. With this, I would like to finish the introduction of Paios. Please have a look at our other videos explaining advanced features and all the modules of Paios. For more information, visit www.floxim.com.